I'm a faculty in the computer science department and honors college. It's a great privilege to welcome Matthew Dickerson today. He comes to us from Middlebury College, Vermont. He's well, about his background. He's a graduate from Cornell, where he did his graduate work in both computer science and Old English studies. His passion is kind of a wide-ranging, everything from literature through computer science, multi-agent simulations, to environmental studies. He's an accomplished researcher as well as the author of several books. And he's an avid writer, but today he will be presenting his research work on multi-agent simulations in environments that are close to our hearts during life. So please welcome Matthew.
So I can just start out by giving you a little of my own background, where I'm coming from, so you know my approach to the whole question we are looking at today. Because I claim to be an expert in complex systems, but I do have some areas of expertise that I hope are helpful. So I want to begin just giving you my own background and how it impacts my approach to the problems that I'm looking at. And then we'll go from there. I'm going to for those of you who aren't familiar with the terms or maybe approach this from a different perspective than the computer science perspective, which is my perspective, I'm going to try to define what I mean by both multi-agent simulation and individual-based modeling. I would guess that a lot of people in this audience have very good ideas or very good definitions of what these are, but I will go over what I mean by those terms and why we should be interested in it, some motivation. I'll give a few examples from both the natural and social sciences of some individual-based models or some multi-agent simulations. And I'm hoping to take a little bit of a look, even briefly, at my current research project, which is in collaboration with Kenrick and with Ward Testa from UAA. And then if there's time, I'll end with just a quick look at a particular programming language that I also use for my own work. And again, if there's interest, how many here are familiar with the NetLogo language and use it? So maybe it'll be worth a quick look at that language and integrated development environment, or IDE. So my own background, I am a computer scientist, and my specialty is in algorithms and data structures. My PhD dissertation, now a quarter of a century ago, was in algorithms in computational algebra. Mostly, though, that was the strategy of picking an advisor and working on whatever the advisor wanted me to do. So I picked a really good advisor. It's the old, I won't go into the importance of the right advisor. But as soon as I finished my PhD, my real interest and my real love was in computational geometry. So algorithms and data structures for problems that are in some sense inherently spatial, geographic, and geometric. I've done a lot of work in Voronoi diagrams and proximity problems. So algorithms that determine relationships having to do with, again, space, proximity, distance, and geometry. So I've worked on research problems, published papers over the years relating to geographic information systems, medical imaging, so issues like how do you take a bunch of two-dimensional cross-sectional slices of some object and put them together to form a three-dimensional model, pattern recognition using computer vision, and some work in robot navigation. So then the question is, how did I end up getting involved in multi-agent simulation? And the answer to that begins about 9 years ago. 9 years ago at Middlebury College had a visiting scholar for one semester, Rob Axdale. And if those of you in complex systems, particularly in complex adaptive systems, may be familiar with his name. At that point he was working with the Brookings Institute. He's now with George Mason in the Department of Computational Social Science. And he came to Middlebury in 2004, right before my last leave, or my second to last leave, and taught a course in the economics department, but he also taught a course, even though the economics department was a sponsor, he taught a course in my computer science department on complex adaptive systems. And I got very fascinated with the work that he was doing in that area, and in particular he had a recently published paper in the National Academy of Sciences that was an individual model-based paper on population growth and collapse in a multi-agent model of the Cayenne to Anasazi in Longhouse valleys. And he was looking at an individual-based models trying to understand the population dynamics of the Anasazi people in Arizona. So I found his work very fascinating. So in 2005, 2006, I devoted much of my leave to some kind of a little bit of a transition in my own research area. I'm still working in computational geometry, but I spent some time studying individual-based modeling and multi-agent simulation, learning an individual-based modeling language, and developed a course at Middlebury College and began teaching multi-agent simulation at Middlebury College. The first courses I taught were actually for the economics and environmental studies departments. But recently we've fully integrated that course into our own computer science department. I also began doing some research collaboration with Middlebury colleagues, primarily in biology. And one colleague in particular working on an individual-based model of the competition between mahogany and other hardwood species in the Amazon rainforest. And his research question was essentially how much logging of mahogany can be tolerated in this rainforest before, without mahogany essentially being completely wiped out. So that was his research project. He had a lot of field research, and he's trying to turn his field research into a viable individual-based model. I just finished my more recent leave, and with the help of an NSF-funded grant, have continued to put more work into teaching multi-agent simulation, seeing it integrated more into university and college curriculums, and also spent a lot of time doing research in killer whale modeling, again with my colleagues Kenrick and Ward. So that's a little bit of my background of where I am coming from. So I'm going to give just a kind of few of my own definitions for computer modeling, or what I think are good definitions, and launch into a little bit what multi-agent simulation is, my understanding of what it is, or my approach to it, and why I think it's interesting with some examples. And we'll just turn more fully to just looking at some examples. Again, how many of you consider yourselves people working in multi-agent simulation in particular? Okay, so 3 of you. So hopefully I won't bore the heck out of you, or anything else out of you. A model is a simplified representation or abstraction of a real system. And computer modeling, of course, represents some real-world phenomenon, or you might think of some real-world system on a computer through the use of mathematical models. Fairly simple definition, I think. Models are used to simulate the behavior of the system being modeled. And one key point that I frequently like to point out is that all computer models are based on simplifications or abstractions. And the goal of modeling, and this is where my undergraduate students at Middlebury College always get frustrated when this slide comes up, but the goal of modeling is not realism. And this is a little bit counterintuitive. The students are always hoping when they take the course that somehow through computer modeling they will achieve full realism of the system being modeled. Modeling always involves constraints. All models are imperfect, and all models involve simplifications. They involve abstractions. So a model must not be viewed merely as a representation of a system. So again, I think often the students in my classes think that the purpose of a model is merely to represent a system, or an attempt at a realistic representation. But rather, all models must be viewed in light of a very specific purpose, goal, or research question. What are you trying to learn or gain or give insight into? And that's the question that ultimately defines what simplifications you can and must make. So the simplifications or abstractions that you make depend entirely on what that research question is. So different research questions about the same system will lead to different abstractions. They will lead to different things that you can, in some sense, ignore. Aspects of the real world that you can ignore, that you can simplify out. We'll give it, again, I'll give some examples of this. The nice thing is that even very simple models with lots of abstractions, lots of real-world information that's simply ignored, may often lead to better solutions to problems or just a deeper understanding. So that's a quick overview of modeling. The next question is, well, what separates what I might call traditional modeling from agent-based modeling or multi-agent simulation? Actually, computer modeling or computer simulation was one of the main driving applications 40 to 50 years ago in the development of modern high-speed computers. So computer simulation really is one of the earliest areas of research on computers. So it is a large field. What I might call traditional simulation attempts to describe some entire system using global mathematical models. So these mathematical models or mathematical descriptions or systems of equations are equations which describe the system as a whole. And in particular, they may describe typically in discrete time steps, what will the system look like at the next time step as a function of what it looks like at the current time step. So again, the big idea here is that the mathematical models describe the system as a whole. Traditional models are often very useful. I have to point this out because I'm often speaking to an audience who are committed to traditional computer science models, and I have nothing against it. They're very useful. They might even be useful far more often than individual-based models. But there are many systems in which real-world phenomena for which comprehensive mathematical models are either too complex to capture or describe, or they're simply not known. And again, I'll give some examples. So, an alternative is what are called agent-based modeling. Often the behavior of the system as a whole emerges from the behavior of a collection of individuals. That is, autonomous agents making their own decisions rather than rules governing the entire system. If you think of something like the relationship between pressure and volume and temperature in a closed system, you could model that based on the individual behavior of molecules, but you don't need to, because there are global equations, well-known global equations, that capture the relationship between volume, pressure, and temperature in a closed system. On the other hand, there are many systems for which that doesn't hold, and we'll take a look at one in a minute. We might be able to directly describe algorithmic rules for individuals, but not for the system. And again, most biological and social systems fit this category. Physical and chemical systems often fit a category where a global model works. Or something like weather systems typically are described by global models. Whereas social and biological systems, oftentimes global models don't work. Let me give an example here. It's a very classic example. How many of you have ever observed the flocking behavior of flocking birds such as starlings? And my favorite word is a murmuration. A murmuration is a gathering of thousands to tens of thousands of starlings, often seen only in England, that fly in these massive flocks. And for a long time, people tried to understand the behavior of the flocking behavior of these birds as a global system. What equation describes where they go? But if you can sit and watch a murmuration of starlings, or even a much smaller flock of starlings, and it seems very unpredictable, the behavior of it seems unpredictable. There doesn't seem to be any single starling, for example, that leads the flock. If you're watching a flock of Canada geese, right, there's a leader. And there may be a couple geese that take turns as leaders. But there's clearly a leader-follower model. That doesn't seem to work with starlings. So let's take a look at an example, an individual-based model. Okay, here we go. I love now the task of fitting my screen there. So here's a population of 300 starlings on a screen. I think I can shrink this and let you see a little bit more of that. Okay. And here we have, I'm going to show you an individual-based model. And actually, I'll go ahead and just start running the model. And in this model, let me slow it down a little bit. There are no global rules to describe the system as a whole. What there are instead are rules that govern the behavior of one individual starling. Yes, I know these look like little triangles flying across the screen, but they actually are starlings. We have to imagine the behavior. And the rules basically describe how an individual starling behaves based on its local knowledge. Okay? What does a starling see? A starling sees only a small number of other starlings in a fixed radius around it. And it makes decisions based on that small area around it. And there's also limitations to how an individual starling behaves. How quickly can it turn? How far can it see? How much space does it want is a minimum space from the next starling. But what it also desires a maximum space. How close does it want to be? How close is it willing to be? And if you set a few parameters, and then you run the system, you begin to see that flocking behavior emerge from the decisions of individuals. I'm not beginning with any flocking behavior at all. I simply have 300 random individuals. But if I give them those rules and set them at work, over time, we see that this flocking behavior emerges from the decisions of individuals. And here's, again, one of the most classic examples of a system in which there doesn't seem to be a global equation describing the system as a whole. And yet, if you simply make rules that govern the behavior of individuals and then simulate all the individuals acting at once, you get the global behavior that seems to mimic reality. Okay. There are also certain abstractions going on here. I'll just mention them first. Well, what are, for the audience, what are the things we've abstracted out in this model? Anyone? What? Just about everything, right? There's no wind, right? There's no environment at all. There's no trees, there's no animals, there's no ground beneath the starlings. There's also no age, no size, no sex. The starlings are actually a homogeneous population. So there are all sorts of big abstractions, but if what we're really trying to understand is their flocking behavior, then all of those aspects of the real world are in many ways irrelevant to what it is we're trying to understand. So we can abstract those out. We can get rid of them. We can simplify them only to the things that really matter. How quickly can a starling turn? And what's the desired space around it in its decision-making process? So we'll come back to some more examples in a minute. Let me try to define a few more terms. Since we're talking about agent-based modeling now, as opposed to, again, this traditional global approach, we should ask, what is an agent? And I would define an agent as any entity, and this is a definition from Hanover. An agent is any definition that can be viewed as perceiving its environment through sensors and acting upon its environment through effectors. Okay. We also teach a introductory level robotics course at Middlebury College where students build and program robots with Lego components. And these are things that they're learning, that their robots do those three things. They have sensors to sense their environment. a decision-making capability, and then they act on their environment. Another way of looking at it, a different definition from a couple other scholars in the field, you can say that there are three functions that continuously are performed by intelligent agents. Perception, and the perception is of dynamic conditions in the environment. So that's why this is continuous. The environment is continually changing, so agents need to be continuously perceiving their environment. Actions to affect the conditions in the environment, and then reasoning to interpret perceptions, solve problems, draw inferences, and determine actions. And of course, the third part, as a computer scientist, is the algorithmic part. And that's the part that I'm really studying. What is the decision-making process of the individual agents? And how do the individual decisions result in the emergent behavior of the system as a whole? So we can look at this now not just in terms of agents, but what is then multi-agent simulation? Well, multi-agent simulation simply is multiple agents acting independently. Again, by independently means there's no global or universal control. I can use global knowledge to understand the system. So for example, if I'm running an experiment, I as the programmer can make use of any global information I want to evaluate the system. But the actual running of the system, the algorithms, don't use global information to make decisions. The agents are acting independently. They're making decisions, and here's the key part, based on local environment or local knowledge rather than global environment. Decisions or events are not based on global or system-wide knowledge. And this is, by the way, what eventually got me really interested in multi-agent simulation, not just the applications which I thought were fascinating, but my own background and training for 20 years, since getting my PhD, was in computational geometry. And as soon as you begin to talk about local knowledge or local-based decision-making, one of the most obvious definitions of local is a spatial definition. Objects acting in space or in a geometric world, where their knowledge is based on some sense of proximity. Now, it's not the only definition of local. You could have, if you're a mathematician, you can have an abstract object like a graph. And a graph, abstractly speaking, does not exist anywhere in space. And all you have are vertices and edges. So you could have some other non-spatial definition of locality. But spatial definitions or geometric definitions of locality are the most natural ones. So here's where all my intuition and my work in computational geometry really began to pay off in studying spatial systems, spatial multi-agent simulation, and where data structures and algorithms for working in spatial systems began to be applicable. Again, if there's any questions, by the way, at any point, feel free to interrupt. If you want me to move faster because I'm saying stuff that all of you have already thought about deeply, that's also fine. Agents affect or change their local environment. And then here's the key phrase in multi-agent simulation, is the idea of emergent behavior. Again, the idea is the properties of the system as a whole are studied and understood as they emerge via simulation from the actions of the individuals. So let me just give a few quotes from a few different workers or experts or researchers in this field suggesting why this is an important approach, why this is a valid approach, and when it's really useful. Yuri Walensky, one of the important earlier papers in the past decade, comments that large-scale patterns in the world are usually, and you might disagree with that phrase usually, you might say often or frequently, the result of the interaction of large numbers of small pieces that somehow combine in surprising ways to create the large-scale pattern. Actually, it's probably always true, but sometimes you don't need to deal with the small-scale pieces. The patterns are emergent. There is no leader which others follow, no conductor leading the band. The patterns emerge out of the behavior of individuals and the adjustment of that behavior in interaction with other individuals. And the example we just saw of the starlings is a great, again, classic example of system in which there is no leader. We can even take a step beyond multi-agent simulation. In the Starling example, all of the agents are homogeneous. All the Starlings are identical. They have no history, no age, no sex. They have no weight or size or speed. They're not born, they don't die. Those things are all irrelevant to that particular situation. But we might also even extend multi-agent simulation to a very particular and fascinating area where the agents are not homogeneous, where they're heterogeneous. And these are called not just multi-agent simulation, but a special type of multi-agent simulation called individual-based modeling. And the key things, Grimm and Railsback address this. In the individual-based modeling, individuals grow and develop. So one thing is that they change over their life cycle. So an individual changes. It may make a different decision in the same circumstance later on in the simulation than it made earlier in the simulation, based on its own history or based on the way it is physiologically changed. So they change over the life cycle. They may physically change, but they also may change simply in terms of memory or past knowledge. Individuals reproduce and die in an individual-based modeling. And then the key one is even within the same species and age, individuals differ from each other. So again, that difference may be physical or physiological. It may also be based on their memory pattern. And again, as soon as you say this, I think it's easy to think of real-world situations where you are dealing with individuals and where the heterogeneity is important to what we are studying. And so we can't simply abstract out heterogeneity. I'll quote from Rob Axtell in the paper that I said was this one that really motivated me to get into the field. In terms of his results in this 2002 National Academy of Science Proceedings paper, he mentioned that agent heterogeneity, which is difficult to model mathematically in a global way, turned out to be crucial in their results to the high fidelity of the model. In other words, if they tried to make their model with homogeneous agents, they could not get the model to reflect the field studies or the actual real-world history that they were trying to simulate. It required heterogeneous, that is, real individuals and not just multiple homogeneous agents in order to achieve the results. They also commented, and this applies to even homogeneous systems, a major impediment to rigorous investigation in archaeology, and they commented, is one shared with certain other sciences such as astronomy, geophysics, and paleontology, the inability to conduct reproducible experiments. Computational modeling is providing a way around those difficulties. Grimm and Railsback give a similar motivation. They say, in ecology, individuals are not atoms but living organisms. Individual organisms have properties an atom does not have. Individuals grow and develop, changing in many ways over their life cycle. Individuals reproduce and die, typically persisting for much less time than the systems to which they belong. And that's a key thing. Is oftentimes what we want to study is the system as a whole, and the system may persist longer than the individuals in the system. So a little bit, a couple more motivational slides, and then we'll take a look at some examples, and I'll look at a little bit of the issues I've been facing in my own research. And then again, open it up for questions or discussion. Again, individuals are the building blocks of ecological systems, and this is my own work. I'm in the computer science department at Middlebury College, but I'm also in the environmental studies program. So even though it was work in economics and the social sciences that initially got me involved in multi-agent simulation, for the last couple of years my research has actually been in ecological or biological sciences, working first with trees and forest cessation of mahoganies and other hardwoods, and then most recently with killer whales. The properties and behavior of individuals determine the properties of the system they compose. Now that's true of physics as well as biology, but most physics questions can be addressed without referring explicitly to atoms. I say the large-scale system-wide issues. Atoms are agents, but not individuals. They don't behave differently based on past experience. As far as I know, atoms don't have memory. A hydrogen atom doesn't remember which ocean it's been in and which river it's been in and decide whether or not to rain based on that. Apparently in the last couple of weeks in Anchorage, all the hydrogen atoms have been decided to mix with oxygen atoms and fall on you. Is that correct? So I want you to know that the sunshine that you've experienced the last few days, I brought with me from Vermont. And as soon as I left Vermont, it started raining there. In fact, my son just emailed me and we're having the first snow of the year in Vermont. So you can thank me afterwards. Buy me a cup of coffee or a pastry or something, because I did bring the sunshine with me. Ecologists are interested in such population-level properties as persistent resilience and patterns of abundance over space and time. So things which transcend the individual and yet which are based on the individual. None of these properties is just the sum of the properties of individuals. Population-level properties emerge from the interactions of adaptive individuals with each other and with their environment over time. And a final slide, and then I'll get on and take a look at some examples and talk briefly about my own work. I may not go through all the examples I have here, but we'll look at just a couple interesting ones. Systems are understood as, so here's some principles kind of as a conclusion. Systems are understood as collections of individuals or agents. Dynamics come from interactions of individuals with each other and with the environment. Again, summarizing, no global equations. Instead, we study emergence, adaptation, and fitness. And a key thing is that theories provide models of individual behavior. They're developed from both field research and past knowledge and evaluated experimentally. So field research is typically critical in multi-agent simulations. Modeling and simulation is the primary tool. Models are implemented with computer simulation. But then the observed patterns are the important observations used to test the theories. And so the field studies are crucial for the IBEs, for the individual-based ecologies and models. Any questions in this? And we'll look at some examples. Yes?
I'm a little confused. So you define the agents as the entities with memory, with age, with some really nice.
In an individual-based model, the agents have memories and age. But in general multi-agent simulation, the agents can be homogeneous. They don't need to have. So multi-agent simulation in general does not require the agents to be individuals and have memory and age. But in the narrower field of individual-based modeling, yes, they do.
So the intelligence comes from within the agents then?
So the intelligence comes from
within the agent definition?
The intelligence comes from the behavior of the agents, right? So agents, from a computer science point of view, I say the agents are algorithmic entities. The agents follow a series of rules or algorithms governing their behavior, generally with some probabilistic element to it. So they're not always deterministic. Most interesting systems, the behaviors have some probabilistic element. With 80% chance, I do this. With a 20% chance, I do this. Go ahead.
So the intelligence of, let's say, a colony of ants,
yes,
ant is not intelligent. Yet as a large system, so ants don't have memory. As
correct.
A large system, they do, so it's on a systematic level rather than on an individual agent base.
Well, I would say that the intelligence of the system as a whole does emerge from the intelligence of the individual agent. So in other words, an individual ant does follow a set of rules. So an individual ant is an algorithmic entity. Now its rules may be very simple. This is the beauty of multi-agent simulation. The intelligence, in some sense, there is no intelligence of the system as a whole. All the intelligence you have is the intelligence of an individual. But when you have a lot of individuals acting together based on their own intelligence, even if that's a very limited and simplified intelligence, the result appears to be, you might even say the result appears to be more intelligent than it is. Or that lots of individual ants acting with small amounts of intelligence result in a system with great intelligence. But algorithmically speaking, all the decisions are made by individual agents, So I would say that's where in some sense, algorithmically as a computer scientist speaking, that's where the intelligence is. And that is counterintuitive and it is strange. Is there intelligence in the flocking behavior of starlings? Or is the intelligence in the behavior of each individual bird? Yeah? I don't know. Did I say anything? Did I answer your question? Yeah, let's look at these. Let's look at a couple of these examples. We'll look at this one because it comes from here we go. All right. So, we'll see how much you can see of this screen. This is a simulation done again by Rob Axtell, and it's a study of the notion of altruism and ethnocentrism. And so have any of you familiar with this work, this ethnocentric study? At least one of you is. So you actually probably could have given the talk then. He imagines he's doing a study and he's asking at what level ethnocentricity emerges. Is ethnocentricity inherent? And by ethnocentricity he means the behavior in which you only help other people who are like you. So he imagines 4 different types of behaviors. The altruistic behavior is someone who helps anybody regardless of, you might say, their ethnicity, regardless of whether they are like you. So that would be altruism. On the opposite extreme is egoism. Egoism is behavior that only helps yourself and never seeks to help other people. Ethnocentrism is behavior in which you only help other people who are like you. And then there's a 4th behavior that you only help people who are different. So somehow your desire is to help people who are different from you. So he says, here's 4 behaviors. And the question is, is it inevitable that there will be ethnocentric behavior? Is that inevitable? Does that make sense? So he puts 4 different types of agents in, and the agent's behavior is based on their type. Right? If they're in a grid. So here's imagining agents in a world competing for resources. So each of these 4 colors represents a different ethnic background. So there's 4 different ethnic backgrounds. You've got yellow, green, red, and blue. And you notice they're random at this point. They're mixed. They're not clustered. And there's 4 different types of behaviors represented by the shapes. And right now, the population slowly changes over time. So there is a death rate. There's a number of new immigrants who appear in the system. And initially, when new immigrants appear, there's a 50% chance that they will help those who are like them. There's a 50% chance that they will be willing to help those who are different. So there's basically 1 out of 4 chance that they'll be egoists, a 1 out of 4 chance that they'll be ethnocentric, a 1 out of 4 chance that they will be altruistic, and a 1 out of 4 chance that they won't fit any of these categories. And the question is, do you still get ethnocentric enclaves with this?
Is this near side group? Nearest neighbor?
So they only respond to those around them. So they only see their neighbors. And they can only help their neighbors. And there's the local decision making. So you can run this simulation. And what you begin to see over time is, in fact, as you can see, you do end up with ethnocentric neighborhoods. You can see we've got a blue enclave and a green enclave and a red enclave, so there will be natural clustering. Also interesting down below is who survives if you've got a very, very small chance of mutation. So when there's new births, new entries into the system, there's only a small chance that the offspring will be different from the parent. And what this shows is which trait survives, and the red trait is the ethnocentric trait. So these are the other three traits, and the ethnocentric dominates. They're the ones who eventually get space and compete for space. And because ethnocentricity dominates, you really get this ethnic enclave. So here's the interesting thing that the simulation showed. I'll pause it here. Now I'm going to bring it down to this point. I'm going to, again, set up the world empty. And I'm going to give a 100% chance of anyone new into the system being altruistic. So you would think, initially as the system is set up, that you would not get ethnocentricity, right? So the only way ethnocentricity can come in is with a very small mutation rate. And that would run the system. And again, the greens are the altruistic genes. So we begin running the system, set, go, and you will notice that altruism really dominates there, right? But even if you run the system weighted entirely towards altruism, you eventually begin to get these ethnic enclaves, and the ethnocentrism begins to dominate. Now again, these are emergent patterns. There's no global system-wide equation, but instead, individual-based models. Now here, there's not a wide variety of individuals, so individuals don't change over time, well, actually there is mutations, there is changing over time. So a very small chance that one of these agents will mutate and will change. Okay, so there's just a quick look at that. You know what, for reasons of time now, I'd like to just spend a couple minutes talking about my own work, and then we'll go back and look at more models if there's time. But also would like to make sure that I leave room for questions. So here's the work that I have been recently doing for the last year with my colleagues here at UAA. I guess, again, probably many of you know them. And this is a map of southeast Alaska, and those little things that look like starlings are actually killer whales. And what I want to talk about is not so much the research, but the questions that as a researcher in multi-agent simulation, or in actually specifically in individual-based modeling, that killed me. I accidentally just quit it.
Those are individual whales, not pods of whales?
Those are individual whales. So the whales are modeled as individuals. I have to start. All right. Give me a moment. I accidentally just quit that. And I want to start it loading again while I go over some of the questions so I can show you one demo from that. buried way too deep. This is why I had all this work before the talk began, and my changed slides, unfortunately. All right. I'm loading my world again, so there's some other models that we have time I want to look at. Briefly look at making spatial a non-spatial individual-based model. So when I came into working here, Kenrick and Ward also already had done a lot of the real hard work and had and again, probably many of you who know them are familiar with their work, had an individual-based model of killer whale behavior, studying killer whale predation, and had done a lot of the work to make, I think, a very, very nice and elegant model. It was fundamentally a non-spatial model in that the whales didn't exist. The whales were individuals. They did change and grow and adapt over their lifetime. And their behavior did, in some sense, depend on them as individuals. But it was non-spatial in that all the whales simply existed in Southeast Alaska, but with not any particular location. And their interaction with prey and their interaction with each other, including mating behavior, the formation of pods, the breaking up of pods, didn't take into account any particular location. And so what Ward Tester was particularly interested in was making this a spatial model, an explicitly spatial model. And one of the reasons is one of his research questions is the localization of prey populations. In particular, for example, stellar sea lions. And the stellar sea lions, they are very much tied to, like salmon, tied to the particular home ground, right? Their rookeries where they were born. And if one of these goes extinct, it will not be repopulated by another subpopulation of stellar sea lions. So these stellar sea lion populations are very distinct. And so modeling that as a single global, non-spatial model didn't answer certain questions about the impact on small local populations. So his interest was in making this a spatial model, and that was a research question. So one of the first questions we had to answer is, what is the spatial granularity? What identifies a single discrete place in space, a single discrete spatial unit? In NetLogo terms, we call these patches. Then what we eventually settled on was a patch of approximately 0.6 kilometers by 0.6 kilometers. That would be a distinct, discrete spatial unit. And one of the issues is that for efficiency reasons, we cannot model individual prey. We can model individual whales because the number in the system is going to be in the low hundreds, whereas the number of prey is going to be in the hundreds of thousands to millions. And there's no way, efficiently speaking, that we can model that many individual prey. So what we do is we model simply a prey population at each discrete environmental unit. So each patch has a number of each type of prey that are present there. And so the question is, what's the size of what is the spatial granularity? Part of that was simply a practical issue, right? You might think that the smaller the granularity, the finer the granularity, the more accurate the system becomes. But one of the issues is there are immediate implications of spatial granularity to temporal granularity. As soon as we see the spatial unit is 0.6 kilometers by 0.6 kilometers, one, it means we have roughly 1 million. We have 663,000 discrete spatial units in the simulation. So any algorithmically computer scientist, in terms of efficiency, that means anything which is done to spatial units, you've got 1 million steps. If you're computing proximity information, you have an n-squared algorithm, you've got 1 billion operations every time you want to compute information about the environment. Other implications are also to temporal granularity. The original model, a time step was 1 day. But if whales can travel, in the neighborhood of several hundred miles in a day, and your temporal granularity is a 0.6 kilometer unit, it no longer makes sense to have a day, a temporal unit of 1 day. So this almost immediately meant that we had to make the temporal unit 1 hour or something on that neighborhood to correlate the movement of whales with the spatial granularity. So here are some of the issues that we faced. Another issue was the issue of long-distance movement. How is it that a whale gets, suppose a whale decides its whale is in one location and decides for whatever algorithmic reason it needs to get someplace else. How does it actually get there? Well, at one level you don't want it deterministic. You want some amount of probabilistic behavior. And one of the reasons you want probabilistic behavior is that will eventually allow whales to discover new places. If every time a whale goes from one place to another, it always follows the same path, there will be no learning. Whales will never discover something new. And that doesn't seem to match the way whales behave. On the other hand, you don't want just heuristic behavior. This is what I call the fjord problem. It turns out to be very difficult to get a whale by any heuristic movement pattern to get from place A to place B without it getting stuck in a fjord. Because in Southeast Alaska, any heuristic that says go from here to there, if I really want to get there, and I just try to move in that direction, I'm going to end up 50 miles up some fjord, stuck. So how do you get whales from one place to another? So this is one of the big problems we worked on. And in a couple minutes, at the end, I'll just show you the results of what we came up with. But what we came up with was a deterministic graph-based approach. So we overlaid a partly random, partly deterministic graph on top of the system and used graph algorithms to optimize, to find an efficient path across the system. But then within that graph allowed a certain amount of wandering, probabilistic wandering. And one nice thing about this, and this gets back to field study, is we can then adapt that graph to actual field data for killer whale analysis. So we can actually look at the paths that killer whales really have followed and make these special nodes in the graph have a higher probability of whales going there if the nodes correspond to places where whales are more frequently sighted. So this is one of the first steps, and I can show you that implementation in a minute. And now my current big problem that we're working on, that I'm now currently working and implementing, is how do whales actually decide where to go? So I've solved the problem. If a whale knows it wants to go from A to B, how does it get there? The next question is how does it decide it wants to go to place B and not place C? And so the individuals will have some sense of memory, and their memory is based on where have they successfully hunted in the past. Yeah.
So the previous, your test path does not access memory.
So my tested path is, it determines that, and I'm going to show this in a minute once this is reloaded. All that does is if I'm at location A and I want to go to location B, here's a path that will get you there. What I then allow is some wandering off of that path up to a certain amount. In fact, they can completely leave the path with small probability.
But the agent's actions are not recalled to help inform its next action, correct?
So that once the agent has made its decision, then it calls this to find what that path is. The harder question is how does it make that decision? So I've solved the fjord problem, but now I'm getting more into the whale's behavior. So there's all sorts of different models that we've already experimented with to look at this, and the current model we're working on is to remember previous hunting events linked to granular time and space. So you simply break the world into a bunch of grids, and you break the year into a bunch of discrete seasons. And every time a whale successfully hunts, or every time a whale hunts successfully or unsuccessfully, it simply remembers the general region in which that happened and the general period of the year in which that happened. And those become a very large collection of memory events. And so every time then the whale decides, there's no hunting where I currently am, I need food, I'm hungry, I need to travel someplace, it checks its memory and says, what are all the locations in the current season? And then it balances how far it would need to travel with how good its remembered hunting is in that location. And the system will allow you to decide what that level of granularity is. So the smaller those seasons are and the smaller the spatial units are, the more memory will be required. In some sense, the less efficient it may be, but you might also expect it to be more accurate in selecting a particular hunting ground. And the last question is, and this is one we were actually talking about, Martin and I were talking about earlier, is even the question of, well, how do you seed the whale's memory? It doesn't make sense to begin a simulation with a whole bunch of whales that are 0 years old. You want to begin with an existing population, but what's the memory of that existing population at the beginning of the simulation? And two competing approaches that we're experimenting with both of them are, one approach is to initialize every whale randomly with the memory based on global knowledge. But every whale will have a different memory. So suppose that globally I happen to know here are 500 different seasons in which there's going to be prey available. And I give each whale a different 51 of those as its initial seed. So every whale will begin with some certain number of memory items already in its memory based on how old it is. Another approach is to simply run the simulation for a certain number of years and let the whale learn its memory, but with no impact. So essentially remove all physiology. The whales don't get born, they don't die, they don't get hungry, they don't gain weight, they don't lose weight. They simply explore the world, remember events as though it were a real simulation, and after some certain startup period, a bootstrapping period, then the simulation actually begins. So both of those will be random ways, very different random ways of starting a simulation. So here are some of the issues that we're dealing with, and it's for me a fascinating collaboration because I knew nothing about killer whales 2 years ago. I know a lot about spatial data structures and spatial algorithms. And it's been, again, very interesting for me to not only work with Kenrick and Ward, but then to go down to the NOAA National Marine Mammal Lab in Seattle and sit in a room with 8 marine mammal experts, share my simulation in progress, and hear them respond to it. And hear, at least a couple experts who know tons about whales and do very little in terms of thinking algorithmically. And all they do is they look at my model and they respond entirely with anecdotes. Like, well, that won't work because I remember a whale who did this. That was very different from what your whale does. So these are some of, for me, the underlying interesting issues. So let me open up. I've rambled on for about an hour. Let me open it up to questions, and then at the end I'll show my interesting underlying, travel path question. Yeah.
So the killer whale study, what is the basic research question?
There are a few basic research questions, but the real basic research question is what assumptions about killer whale prey choices will lead to the the field studies about population dynamics over the past 20 or 30 years.
So things like pod formation behaviors, hunting behaviors.
Pod formation behaviors, hunting behaviors, in particular, prey selection behaviors.
Right.
So which prey selection behaviors will lead to the sort of killer whale predation that has impacted prey populations? For example, we know that there have been stellar sea lion declines in certain localized areas, but not in other areas. Are there assumptions that one might make? We don't know if the assumptions correspond with how whales really work. But are there assumptions that we might make about killer whales that would account for prey population dynamics that have been observed?
And this is a two-dimensional model, and they live in a three-dimensional world. Does that have any...
Yeah, so fortunately whales don't fly.
Exactly, well, true. But they dive, and so does the
They
prey.
do dive, and they do hunt below the surface.
Right.
So one of the problems with field studies is that how much whales actually eat, how much killer whales actually eat, some of it has to be inferred, because you actually rarely, a lot of a whale's hunting, you actually rarely see the kill. Yeah. What you see is oil slicks on the surface from a dead seal or a dead gray whale. Even it's unknown, for example, it's believed that if killer whales kill a gray whale, which is much larger than a killer whale, they won't even be able to eat all that gray whale. They might spend a day feeding on the gray whale, and eventually it's going to sink below where they're feeding. What percentage of that gray whale will they get? So that's the case where I simply have to read the killer whale research and assume that the killer whale biologists are making reasonable guesses. And those reasonable guesses, I say reasonable guesses, based on field research, are what I incorporate in the model. Yeah. So fortunately, I can trust Ward and his group of experts on that. And a lot of that, actually, I was able to inherit from Kenrick's model. The non-spatial model already fortunately dealt with a lot of those important issues. So the whale physiology, how much they eat, how much energy they get from each kill, that I didn't have to start from scratch on. All the spatial issues are what I've really had to wrestle with. And we have these periodic conversations every couple months, Warren and Kenrick and I, and when we get to the new decision-making process, yeah.
In your spatial world, you have land and water.
Yep, nothing happens.
So somehow you're defining coastline.
Yes, exactly.
So the movements are always in the water parts.
I don't let my whales travel across land.
How do you define those coastlines as particular cells, or are they as vectors?
Yeah, so great. So the very first thing I do is I input the map, and I actually have two different.
Is it a library of grid components?
So there's actually two different ways I can input a map, and I can do it either way, and they're both equally inefficient. I can input a map simply by reading an image, a GIS map. Reading an image, I take a black and white image that's land and water, and I interpret that as land and water, and any patch that has a mix of black and white becomes coast.
Okay, so
or any coastal, any land or any water that's adjacent to land, I interpret as coast. So I'm abstracting away depth information.
I know they are.
And I can also directly read a GIS file, which is a vector-based file. So my software has the capability to do that. And I thought it would be more efficient, but it turns out that these vector-based files are so complex that it's no more efficient than just reading the image. So I make some assumptions.
There are ineligible grid cells that a whale cannot move to.
Any land cell it can't move across.
Do they make
the field problem?
And when they move from one grid to the other, is it only left, right, or north, south, or can they move diagonally?
They can move any direction.
Okay.
So actually, a whale's location is not a discrete cell. So a whale actually has in some sense, within the accuracy of floating point arithmetic, a whale actually has an exact location. So a whale is not just in a cell. A whale can be any location within the cell. So a whale can move across a cell. That does not affect prey dynamics, because prey are discrete within a cell.
Right.
But it will affect how far a whale can move in a day, and it will affect how close whales are to each other.
When do you test to see if it's moved to an ineligible cell?
I never allow a whale to move into... So the whale movement...
Does it make the move and test it, or does it test first and then see if it's
well, in some ways it's irrelevant because they're not real whales. So my system looks at all the possible moves and makes a choice of where it's going to move based on all the possible moves.
Okay. I did some random search theory. The Navy did that many years ago.
Yeah.
And I ran into that problem of what is an eligible move and what is an ineligible move.
Yeah.
And I suddenly found out it was much more computer efficient to make the move and then ask the question, is that a valid move? If it isn't, start over and do it again.
But functionally,
versus
that's
the
what
opposite.
I do. I don't actually redraw the whale in that new place. But if a whale is going to make a local move, the first thing I do is say, what are all the possible places that it could move? And I rule out the ones that it couldn't move to. So in some sense, I'm testing all of these possible moves. Or, more realistically, actually, often I'm trying to go in a particular direction. And I say, is there land in that direction? And if there is, it adjusts its movement accordingly.
Okay,
So in some sense, functionally, I'm actually having to do that. But you wouldn't actually see the whale move in every possible way that I'm testing. Yeah.
How do you introduce something like sound, which is essentially a whale's space. Now,
So-
the ship moves through, they start
Yeah.
drilling, it's all not as steady as land.
No, so one of the things I abstract away is that I'm not trying to model whales explicitly communicating to each other. What we do model is a range at which whales can sense one another. So if two pods pass within a certain distance, or if there's a kill, if one pod makes a kill, then we know that whales sounding that they've just made a kill, sending a call that they've just made a kill, will reach a certain distance and will attract other whales. So we don't explicitly model that whale call.
No, I'm thinking more in terms of, well, since you mentioned whale calls, if you've got a large propellered ship,
Sure.
or a drill rig, or
Yeah.
some other
Yeah.
sound thing that interferes with whales' communication.
Abstracted completely out of the system. So there's no human involvement in the system. Now, where that would come in, however, and where we could account for that is the underlying graph along which whales move can in fact be based on observed densities of whale movements. We have a lot of data of where observed whales have moved, not only from visual observation, but from GPS tagged whales. So in fact, a whale might not move along that path in real life on this particular day because there was a ship going through that veered it off. But statistically speaking, if there's a path in which ships frequently travel, and therefore whales avoid those paths most of the time, then that will eventually make it into the system based on field data. Even if I've abstracted away the details of one individual ship, the implicit knowledge we hope makes it into the system based on field studies of where whales actually move. But in fact, there's no way that we could represent ships moving around the system or anything like that. And if there are some places that whales don't ever actually go, and I've actually talked to whale biologists, and at one point a whale biologist looked at one of my cats and said, oh, a whale would never travel there. She just knew. Instantly. A whale would never actually travel there. She didn't tell me how she knew that, but she was convinced of that. That would actually be pretty easy to put into my system. Don't let the whale travel there. Make my graph, just remove that edge. So there's no graph edge there. Or it wouldn't say a whale could never move there, but it would be a very, very unlikely random event. I mean, killer whales do occasionally travel, 20 miles up rivers, and they appear to be lost. So there is some small probability of the whales getting lost. But that would be not explicitly modeled, it would be abstracted out of the system, but we hope it would be implicit in the field studies and the underlying graph algorithms. Yeah.
So the whale position is not discretized. It can be anywhere.
Correct.
But the environment is discretized.
The environment is discretized.
And so it has a certain healing length to the prey density or in healing time to the prey
Yeah, okay, so here's a great questions. So every patch is one of three types. It's water, it's coast, or it's land. And I also store for every patch how close it is to the nearest coast, the direction to the nearest coast, the direction to the graph. Every patch also has all the prey numbers for every different type of prey in the system. And that's initially based on field research. So we have a lot of accurate data. There's a lot of raw data available with seasonal variation of the prey. There's also a flag that when a whale has been hunting in a certain area, that the prey go into hiding for a certain amount of time. And when the prey go into hiding, the success rate of hunting in that patch becomes much lower. So that would be something very spatial. That in a particular area, when a whale has been hunting and have made a kill in that area, the prey hide.
In that area is just within that grid, or does that spread?
So that's a constant that can be built into the system. There are several constants that can be built into the system that we can then adjust, and hopefully you don't have to adjust too many constants in order to match real world data. But those are adjustable constants. One is how far away will whales travel to join in the drill. And another constant is how far away do prey sense to killer whales. There's a constant system, very easy to change, and the idea of whales hiding, of prey hiding is built into
Well, the fact that you say that's one constant means some exponential function spreading out from the position of the whale.
a lot of the constants, a lot of the equations are actually two constants, one of which is the exponent in an exponential distribution, is correct. But some of them are not. In some cases, we hope that there's a simpler equation that we can abstract out the complexities. Yeah. Yes?
Two questions. One, do you ever factor in tidal variations, since that's I would think, that impacts like salmon migration, which is
Sure.
prey, and also what's your confidence factor as far as for your model to looking at, here's reality out there for that whale behavior. Are you looking at 90% confidence level, 50, 75? Just curious.
Well, so the tidal things we're not taking into account. We're only looking at transient killer whales, which don't feed on salmon. They're only mammal-eating killer whales. Unfortunately, we don't have to deal with salmon. Otherwise, my prey numbers would be off the charts. There may be hundreds of thousands and millions of seals, but there are hundreds of millions of salmon. Hopefully, there will be a couple fewer as of Saturday morning. I make it down to do some late season silver salmon fishing on Monday. I just distracted myself thinking about fishing. The confidence level. You can ask Kenrick what the confidence level is. I think they have results in the non-spatial model that very accurately reflect real world field data. I think it's much too early in the spatial model to answer what our confidence levels are. There's a lot of aspects of the system that is based with I think very high accuracy on field studies. There's a lot of things that are not known. It's very expensive to tag whales, and typically the tagging of whales gives you maybe a month of data, and then visual observation of whales is typically confined to summer months. So there's much less known about whales and killer whales, transient killer whales in particular, in November, December, January, February, March. So I would say we have a very low confidence level, and one of the things we're looking at right now in the model is to actually, in some sense, shut down the system, to sort of statically remove killer whales from the system during a certain period when much less is known about them, and simply stochastically determine death rates, birth rates, interaction rates, without actually explicitly modeling. So that's one possibility. During periods and times in spaces where much less is known, not trying to model that explicitly. So those are some of the big questions that are open. I don't expect this model to be done in the next weeks or months. I've been working on it for a year, making a lot of small decisions and testing things. I'm looking at this as a longer term project. So I'd love to say 100%, but realistically, it's probably 5% right now, and that's growing as we go. I was very fortunate again to have some of the work done already for me. So a lot of the physiology done before I started. Yeah. Yes.
Going to the whale's decision-making process for finding prey, what is the prioritizing factors? Like, is it prioritize like the distance of some prey that's memory based?
The first and highest priorities are actually fatigue level and hunger level.
But I'm saying, let's say there's like two locations, like A and B.
Yes.
A is twice as far as B, but it has like twice, it has a much higher success rate in its memory bank.
Correct. So we basically have a formula that would look at the expected cost and the expected result and balance those two things. And that's a formula that's flexible enough to very easily adjust over time. But right now, I think it's probably pretty much a simple linear formula, but easily adjustable later. how far will we have to travel to get this food, and what do we expect to get there? I think I probably can't answer with detail what that exact balance is, because I think the formula looks at both of these things and makes a decision, with some probabilistic element too. It's not all deterministic. And so we have to run the simulation many times in order statistically to get a trustworthy result. So those are decisions I'm putting a lot of flexibility into the system right now to make them easily changeable later. That one weighting formula or balancing formula. That's kind of buried down in a single procedural statement in the formula. That I can change that statement really easily and potentially completely change the result. But that's one of the decisions that it's easy to put off until everything else is working. Any other questions? Let's just end with let's see if we've initialized a world. To just show the so somewhere here, there's a starting location of the path. Let's move that up to here. And there's the ending location. So there, for example, is the path that we follow to get from here to here. Now, just explaining what's happening. Here is where my underlying graph is. It's finding its way to the nearest node in the graph, following that to some graph location, which I think is probably right there, that last little hook, and then leaving the graph and going to another node. So it's about keep in mind there are about 660,000 discrete units there. I have a graph of about 1,000 nodes. So every graph node, there's one graph node to every 600 patch units. Among those graph nodes, there are 60, a much smaller number, 65 key anchor nodes, and every path will go through one of those anchor nodes. So that's the spine of the graph. And I can then adapt this to field research by hand-picking those anchor nodes to correspond with density of actual whale sightings in the real world. So let me find a more complex path here.
What are the boundary conditions?
What?
What are the boundary conditions on the edge of this map?
This is essentially the study area of southeast Alaska where the
So what if a whale? So a whale is never going to go to the extreme southern edge and go off the map, or to the far right and left edges.
Well, the answer is, if they do, we cease to model them. So actually, one of the things we're looking at is a certain percentage of the whales leaving the system in November or October and re-entering the system in February. Because they seem to go off this world, some percentage of them, and hunt down around, say, Vancouver Island, or even northern Seattle Sound area. And so what we do is we simply remove them from the simulation. The individuals are there, but they're being represented as being off-world. And at that point, we're not modeling their behavior in the system. We're simply stochastically saying there's a certain percentage chance of them gaining weight, losing weight, dying, giving birth, etc. But not spatially within the system. So let me just try another path. Let's just see how it deals with fjords. We'll start it right here. There's another small problem with having there we go. I think I'm not going to be able to give you a really good visual test with a resolution screen so much smaller than my computer. Any other questions or arguments or disagreements? Angry rebuttals?
The zigzag path towards the termination.
Yeah.
Those are the anchor nodes it's traveling between?
So, there's a graph somewhere up here, and I can actually display it if you want.
Oh.
If you want to come up and look at it, actually, it'd probably be easier to see it on my computer. I can display the underlying graph. I can display the underlying anchor nodes to let you see. So what it's doing is it's finding its way to the graph. It's traversing what's guaranteed to be the most efficient path on the graph using a Dickerson algorithm, which is probably bringing it to here. And then it's got to get back off the graph to there. So globally, this is not the most efficient path. And if you're looking at two very close points, you can see a lot of path inefficiencies. If it's traveling very far, the further apart the 2 points are, the closer to optimal that path will be. So what I guarantee is the path on the graph is the most efficient path on the graph. What I don't guarantee is locally that it's a very efficient path because it's got to find its way off the graph. So there are some real trade-offs in this. In doing this algorithm, and I wouldn't say this is going to absolutely the final movement algorithm, but we experimented with, I think, 8 different movement algorithms, and this is the one that experimentally seemed to work the best. Heuristics were just very inefficient to throw in all the special cases to avoid the fjord problem. The general directional heuristics just did not work very well. All right. If you want to come up and take a look, I'll show it to you. Otherwise, thank you, and I'll be around for a little while. If anyone wants to chat more. Thanks a lot.